All right, today we're going to jump ahead a little bit and do some piecewise and step functions, special type of functions I want to do with you. And then we're going to come back tomorrow and do inverse functions a little bit. I was going to do those today, but I think this would be a little bit easier for you to comprehend. And then tomorrow we'll do inverse functions, and then we're all done with chapter unit 2, and we'll be ready for a test on Wednesday. So I'll get you a test review out tomorrow. So that's kind of our schedule for the week. All right. So let's do some special type of functions. Let's do special. I'll just call them special functions. And modeling. Okay, now one type of these we're going to look at, you've already kind of done, so that's why I thought that would be pretty easy for you to do. And you didn't really know you were doing it, but we did it. So first of all, let's say we have a parking lot here. Consider this. We have a parking lot that charges $3 for the first hour and 50 cents for each hour thereafter. Okay, so let's take a look at this. I want to make a little chart here. So here's our cost. So for the first hour, they're going to charge $3. So say you park for 15 minutes, right? That'd be a quarter of an hour. How much are they going to charge? Well, they're going to charge you $3. Let's say you park for half an hour. Well, $3. How much for 3/4 of an hour? Well, $3. Okay. So the question is, what about for an hour? Well, after 1 hour, they're going to bump you up. $3.50. Okay. And then an hour and a quarter would be $3.50. But when we get to 2 hours, that'll be $4. So here we'd say, well, first of all, is this a function? The answer should be yes, because for each number in a domain, there's one number in the range, right? 0.25 has 3. It doesn't have any other number, so it's definitely a function. And your domain could be x values greater than or equal to 0, because you could have any fraction of time, right? It's the y values that are the range that's interesting, because the range is going to be y values that are greater than or equal to 3, but it's either going to be 3 or 350 or 4 or 450 and so on, right? So it's not consistently changing decimal wise. It's 3, 350, 4, 450 and so forth. That's what the range is going to be. All right, so it's a little different. Now this is a function that obviously we haven't done anything with, right? So how do we graph something like that, or what kind of a function takes on this kind of a or would model this type of situation? Well, there's one called the greatest integer function. And it's symbolized a couple different ways. You might see it like this, or you might see it like this, okay? And a greatest integer function basically rounds down. So if you have a number from 0 to 1, all right, not including 1, it's going to round down to rounds to 0. If we have 1 to 2, right, not including 2, this is going to round to 1. So it takes whatever that decimal part is, and it's just rounding it down. Okay, so it's rounding it down to 1. All right, that's what the greatest integer function does. So if you have the greatest integer function of 3.8, that's going to equal 3. It's rounding it down. All right. So this is sometimes looks like, well, let's go ahead and graph it. So let's go into Desmos. And graph it. So where do we find this in Desmos? Well, first I'm going to go y equals, because I like to do that. We're going to find it in functions. Now, it doesn't look like it's integer. They don't use int, but they use something called a floor. All right, so if we go floor of x, we get that. Now, it's kind of interesting to use this terminology because floor is down, right? So this function is going to round down. And we might notice that we have some steps, right? So this is sometimes called a step function, right? See here, this one rounds 1 to 0, okay, but it's not including, it includes that little 1. Let's see if we go up here to anything over 1, all right, it's rounding it to 1, okay? So 0 is also rounded to 1, excuse me, to 0, okay? But anything close here, you can see on the negative side, is going to round down. So let's go to 2, and 2, see, it doesn't quite get there, but right at 2, it's 2. So I think this is just a little bit maybe misleading. You see how that 1 is 1, all right? So it gets really close to 1, it rounds to 0, but not quite 1. So you have to be careful with that, all right? So because 1 is going to go to 1, which should make sense because there's no way to round it, right? So it's just going to stay at 1. So this is actually should be an open dot here and a closed dot up there, all right? So that's what the floor looks like. So we have these steps, all right? Domains, all real numbers in this case. Range is going to be integers because we have 1, 2, 3, both directions, positive and negative. That's what this particular function's domain and range is. Okay, now let's do this. Y equals, go into functions. Let's take a look at ceil. Now ceiling, you can see, it's just kind of the opposite of floor, because if we go like this and we take a number between at 0.25 or whatever, it rounds it up. So in this case, we're rounding up, right? So 1's going to go to 2. Okay, so it's rounding it up. All right, so floor is rounding down, ceiling is rounding up. Kind of makes sense. All right, still a step function. Domain and range is still the same thing as floor. It's just that's how these functions work. Okay, and these are called step functions because obviously they form steps. All right. There, you might have seen, well, what about, wasn't there one more? You might say, well, I thought I saw one more in here. Well, that's round. Oops. Let's get rid of that. Put it down here. Okay, y equals, and then we'll check that out. There's round. Okay, and what does it do? Well, as we would suspect, rounds just like it normally does. So 1.5 is going to bump up. Anything close to 1.5 is going to bump down. Okay, that's what round does. It uses the normal rounding rules that you were taught a long time ago. Okay, so we have 3 basic step functions: floor, ceil, and round. Right? We're trying to model this problem though, right? So since we're rounding for the first hour, we want to decide, well, which one would I use? Would I use ceiling, floor, or round? What do you think? Hopefully it's not saying round, because round is rounding to a nearest 0.5 or something, and we definitely don't have that. We have something that looks more like this. All right, so this is actually can be modeled using a floor function. Let's take a look at it. I want to get rid of these. So let's take a look at our floor function. First of all, what if we went like this and put a +3 on the end of it? All right. So now notice that, of course, we're not interested in the negative part, that when at 0 hours, when I first walk into the place and park my car, even though I haven't parked there, if I left it, they're going to charge me $3, okay? Any time along this line here, this little step, all right, I'm getting charged $3. But as soon as I go to 1, right, then I'm moving up. But this has me move up 1 when I really don't want to move up 1, right? Because it's only 50 cents afterwards. So let's think of our transformations a little bit. Now we've shoved this guy up 3, but what would we want to do now? How can we get it so that it's not jumping up by as much? What transformation would that be? Well, let's try a transformation that does a vertical stretch or compress. So what if we put a 0.5 in front of my function? Now, notice, yep, I'm still getting the 3 values that I'm looking for. Give me a point on there. Okay, but as soon as I pump up here, it's 350, 4, 450, and so forth. So I've taken the floor function and transformed it, just like we talked about last week or a week ago, and got it to model my problem. All right. So there is the floor function. All right. So let's go f of x. Oops. Put it down here. F of x equals 0.5. Floor, greatest integer, whatever you want to write. Okay. It'd probably be more proper if we did this. Okay. Where that's the greatest integer function. All right. So we model that, and that's a step function. So anytime we have something that has those steps, it can either be modeled by using a floor in Desmos, a ceiling, or a round. All right. But mathematically, we're usually talking about the greatest integer, and that's how that one would round. All right. The other type of function is called a piecewise function. And a piecewise function is defined in pieces. Or intervals. Okay, so for example, piecewise function is going to look something like this. Right, and usually you're going to have a condition. So let's say we have x is greater than or equal to, let's go actually less than or equal to -1. Then I would have some sort of an equation I want to follow. Let's follow this. All right. Then when it's between -1 and 1, okay, we would have another equation. And when it's between, or let's say when it's greater than 1, we have another equation. Or I can use the same type. Here, let's go like this, just change it a little. So this is called a piecewise function. And they always have a conditional of some type. Here, and then the function. All right. So let's take a look at this by hand, first of all. See what's going on. X and f of x. So I'm going to pick a -2. So when I have a -2, I'm going to use, since it satisfies this top condition, I'm going to square that and get 4. All right, -1.5 satisfies the first condition. I'm going to square that. Get 2.25. Okay, -1 satisfies that condition. I'm going to get 1. Okay, but as soon as I get between that -1, then I'm going to follow a different. I'm going to cube that. All right, so I'm going to go to my little calculator here. And let's see, I should be able to view a scientific one. There we go. 0.75 to the third. So I get 0.43. Okay, and then if I take 0, I'm going to get 0. And then if I take 0.75, I'm going to get the same thing. Okay, except it's going to be negative. But now, as soon as I hit that 1, all right, now I'm following this condition. So I'm going to get 1 squared plus 1, which is 2. All right, and then of course 2 is going to be 2 squared plus 1, which is 5. So each one of these points, or x values, is going to follow a different condition, and when it does, it's going to get an equation. All right, so that's how you do a piecewise function. They have some applications actually in income taxes. Anything that has some sort of a scale sometimes can be a piecewise function. Okay, so there's some applications for them out there. How do we graph these in Desmos? Well, let's take a look. All right, again, you've done some of this. So we're going to go like this. Okay, so in Desmos, I had to look it up real quick. So it's y equals. Now we need these brackets. So we're going to go here. Okay, so that's 1, 2, 3. Hit the ABC. It's these brackets down here, or the braces, whatever you want to call them. All right, and then we need the condition. All right, I think that's what condition, and then the function. So for our first one, we had -1, and x is going to be less than -1. Okay, now we need a colon, so I'm going to go 1, 2, 3. I hit the ABC, the up arrow, and then this guy here right by the end, that's the colon. All right, so we're going to hit that. Okay, and then I'm going to put my function in a squared like that. Okay, so there's my function for that. Now, comma to separate the next piece. All right, so we put the condition in first. -1. Okay, x, just 1x there, and 1. Okay, got to get that colon. ABC, up, colon. Oops, already got it. Now I'm going to go and put in the function. That was x to the third. Oh, I'm getting 3 things here. X to the third. Okay, make sure your arrow past that. Comma. Okay, now I'm going to put in my last condition. So that's going to be x greater than or equal to 1. Colon. Hit that up. Colon. And then we're going to put in the function x squared plus 1. Okay, so we got this really interesting little piecewise function here. Okay, and in actuality, I'm not sure. Yeah, I guess it's okay. We got a function there, right? Because we don't have a connecting, all right? But as long as we're not equal to -1 here and equal to -1 down here, we're okay because that passes the vertical line test, all right? So this is definitely a piecewise function, all right? Kind of interesting the way it is, but that's how I just kind of made it up, so that's what it looks like, all right? So that's what a piecewise function is. Again, it's made up by conditions and pieces. I don't know if you want some more examples. Because you might remember when you did the one marble slides and you were restricting those, the equations that you made. Those are kind of same idea as the piecewise functions. Okay. So now, in Desmos, you kind of write it backwards in what you do in math. Usually math, we're going to go condition. We're going to go function first and then condition, and these guys are doing it backwards. So we would go, let's just do a line on this one. And then we'll do one like this. All right, so that would look like that. Okay, but when we put it in Desmos, it's going to be reversed. All right, so let's see. X is less than 0. We're going to have 2x minus 3. So it's going to look something like this. Right? 3x plus 5 when x is greater than 0. So it's going to look something like this. All right, so then we've got a solid dot here, but we have an open dot there because it does not include that 0 point, right? Because it's right there, okay? Another piecewise function, right? So I think that's all we need. Let me double check. Okay, so I noticed that in the book, you have to be careful because they use this notation for the rounding down, right, which is floor for us and Desmos, right, but they use this one for rounding up, and they have no feet on the bottom. They just leave it like that, okay, and it's very hard to see the difference, so be careful of that one. This is round up. So this would be like ceiling. So this would be ceiling, this would be floor. So be careful when you're doing those problems, all right? We could take a look at, say, number 25 on page 129, all right? Two, 3, 4, draws this line, and -4, 1, 2, 3, 4, 3, 4, and it starts at 3. Goes up to here. Okay, so they want you to write a function for this. All right, f of x equals. All right, so obviously for this one, okay, we're going to start graphing it at -4 and stop it at 0. All right, and it is a line. Okay, so we know it's going to be a y equals mx plus b. All right. It's a pretty easy, straightforward one because we know what the slope is. We can tell that it starts at -3, 1, 2, 3, 4, 5, 6. So my slope is 6 over 1, 2, 3, 4. Okay, so I got 3/2 x plus the y-intercept is 2, all right, and I'm going to graph this between -4, not counting -4, right, so I don't want to put equals to, x greater than or equal to 0. So we're doing this line, all right, all I did was count the slope, put in the y-intercept at 2, and said, okay, here's where I'm graphing it. Now let's do this one. So the slope is down 2 over 4. So down 2 over 4, which would be 1/2 x, right? Y-intercept's the same, such that start at 0 but not contain 0, and go to 4. All right, so if I type that in, now remember in Desmos you got to reverse it, right? It's a different format. So if we go like this, let me clear this out. All right, y equals, hit the those guys. Okay, so now in Desmos here, I'm going to reverse this. I'm going to put the condition first. So let me go back to this, -4, this way, this way, this way, 0. Okay, ABC, up, got to get the colon. All right, now I'm going to put in the function, which was, what did we say that was? 3/2 plus 2. So I got to go inside here. 3 divided by 2, x, x plus 2. Okay, starting to look like it, right? Okay, comma, put in the condition. So we're going to go 0 this way, x, less than or equal to 4. All right, give me that colon, ABC, and now we're going to put in this one, which was -1 divided by 2. Okay, x plus 2. And there it is. Right, so that's how you would define that. All right. So we're just, to make this graph, we're just figuring out those lines. I didn't really have to do a whole lot except just kind of count my rise and run by changing y over changing x. Y-intercept, changing y over changing x. Look at the condition. All right. Okay, so let's do these problems here. Page 129. All right, numbers. Graphing these piecewise functions to you is going to be that big of a deal because you're going to put some of them in Desmos. I think it's important that you can do a little bit of these by hand, so why don't you do one by hand? One by hand. All right, so you can figure out what's going on there. Okay. 24. We did 25 through 26. 26 looks like a fun one. And then we'll do 28 through 35. Be careful to look for the ones that have no bottom parts or no feet versus the ones that do. All right. And then let's graph a couple of these. All right. And these are going to use Desmos, the floor, and the ceiling ones. So those won't take you very long. So anyway, there's some problems for you to work on. I'll get you a review. We'll do inverses tomorrow. And have a good day.